Welcome back. Today we're taking a deep dive into a really interesting corner of the OEIS, the Online Encyclopedia of Integer Sequences. We're looking at A000296.
Ah, yes, A000296. It looks specific, maybe, but it's quite fundamental.
Exactly. So our goal today is to unpack this one, the number of set partitions without singletons. Now, for anyone new to this, a set partition just means dividing a set into smaller, non-empty groups, right?
Correct, and non-empty and disjoint subsets that cover the whole original set.
But the key twist here for A000296 is that every one of those smaller groups, those blocks, has to have more than one element in it.
Precisely. No single elements allowed on their own. And it's this restriction, seemingly simple, that makes the sequence such a cornerstone in combinatorics. It links up areas you wouldn't initially expect.
Okay, let's get concrete. The sequence starts 1, then 0, then 1, 1, 4, 11, that first bit, 1, 0, 1, especially the 0 for A1, and then jumping to 4 later on. That feels noteworthy.
It really is. The A01 is, well, standard convention for the empty set. There's one way to partition nothing, which is the empty partition itself. It fits the rule vacuously, you could say.
Okay.
But A10 is crucial. If your set only has one element, say 1, you cannot form a block with more than one element. Impossible.
Right. So 0 ways.
Exactly. It perfectly illustrates the rule right away.
That makes sense.
Yeah.
So then, when we get to A4, could you walk us through what those 4 partitions actually look like for, say, the set 1, 2, 3, 4?
Certainly. So imagine you have 1, 2, 3, 4. The 4 ways to partition it, so every block has size 2 or more, are: first, you can pair them up, 1, 2, 3, 4.
Like 2 pairs.
Then you can swap partners, 1, 4, 2, 3.
Got it.
And the third pairing, 1, 3, 2, 4.
Uh-huh.
And finally, you can just put them all into one big block, 1, 2, 3, 4. That also fits the rule. Size is 4.
And that's it. 4 ways. 1, 2, 3, 4, 4, and 1, 2, 3, 4. Okay.
Those are the 4.
Okay, this is where, for me, it gets really fascinating. These numbers, A000296, they show up in places you just wouldn't expect. What are some of these combinatorial interpretations?
Yes, this is where the richness lies. One interpretation is, perhaps surprisingly, the number of complete rhyming schemes.
Rhyming schemes?
Yeah.
Like in poetry.
Exactly. Imagine a stanza where every line must rhyme with at least one other line in that stanza. No line is left rhyming alone. The number of ways to structure those rhymes follows this sequence.
Wow. Okay, what else?
Well, moving to graph theory, it counts stable partitions of an n cycle. Think of points arranged in a circle connected to their neighbors. A stable partition groups these points such that no 2 points connected by an edge on the circle end up in the same group. It's about partitioning the structure without breaking immediate connections.
Interesting. So a structural property.
Very much so. And then there's a connection to permutations that I find particularly elegant. A000296 counts the permutations of 1, 2.2 foremost, where the positions of the left to right maxima.
Okay, wait. Left to right maxima, that's a number bigger than anything before it as you read left to right.
Correct. And it counts permutations where those positions are exactly the same positions where you have descents.
A descent being where a number is followed immediately by a smaller number.
Precisely. For N4, remember A4, the 4 permutations are 2143, 3142, 3241, and 4123. You can check the maxima and descents line up perfectly in those 4.
That is quite a connection. Set partitions, rhymes, graphs, permutations. Amazing. So, shifting gears slightly, how do mathematicians actually generate these numbers? Is there a formula?
There are several ways, but one of the most compact and powerful is the exponential generating function, the EGF.
Right.
For A000296, it's given by XPX1.
XPX1X. Okay.
And EGF, like this, basically packages the entire sequence into one function. You can expand it as a power series, and the coefficients give you the sequence terms, scaled by factorials. It's incredibly useful for deriving properties.
I see. And are there connections to other known sequences?
Oh, absolutely. There's a very neat relationship with the Bell numbers, BAN, which are sequence A0001 lesson in the OEIS.
Ah, the Bell numbers. They count all possible set partitions, right?
Right.
With or without singletons.
Exactly. And the connection is beautifully simple. Bn, the total number of partitions of an n set, is equal to an plus 1.
Wow, so the Bell number Bn is the sum of the number of partitions of n without singletons, which is an, and the number of partitions of n plus 1 without singletons, an plus 1.
That's the identity. It elegantly shows how partitions without singletons relate to the whole picture. It tells you something fundamental about how these structures are built.
So for someone studying this area, or even just curious about mathematical patterns, what's the big takeaway here?
I think the main point is how a single, clear definition, partitions without singletons, can act as a bridge. It connects combinatorics, graph theory, permutation patterns, even things like rhyming schemes. These different views, these interpretations, alongside the generating functions and recurrences, they give us a toolkit. They help us see the underlying unity and structure in seemingly very different problems. It shows the interconnectedness of mathematics.
It really does. An incredible amount of depth packed into just one sequence entry. It's quite something.
It is indeed, and it encourages you, I think, to look beyond the definition itself, to consider how these abstract ideas, these mathematical games perhaps, can model phenomena and connect fields in ways you wouldn't initially predict.
A fantastic thought to end on. We definitely encourage you, the listener, to explore A000296 on the OEIS website yourself. There's always more to discover. Until next time, keep diving deep.